So let's look at a couple of examples for this, and that's going to finish off the lesson. And you'll see that, hey, p-series, piece of cake, in order to apply. So determine whether these series from n equals 1 to infinity of 1 over n converges or diverges. This thing looks like it's the harmonic series, right? Our p-value here is an understood 1, and if our p-value is 1, this thing absolutely diverges. Memorize it, burn it into your brain. Harmonic series, what's it do? It diverges by the p-series test. Okay, here's another one. Determine whether the series from n equals 1 to infinity of 1 over n squared converges or diverges. All right, well, our power here is 2. 2 is greater than 1 by the p-series test. That sucker converges. All right, now we did the improper integral that applies to this one at the very, very beginning of this lesson, and we found that that improper integral converged to 1. And what we've been saying all along is that when we're using the integral test, just because that improper integral converges to a particular finite number doesn't mean that that's what your series converges to. As a matter of fact, Euler, maybe you've heard of that guy, he's got a lazy eye there or something. Euler showed that this series actually converges to pi squared over 6. Okay, so let me kind of show you this with some pictures, not specifically this pi squared over 6. If you're interested in where that comes from, there is a separate video, MathLogic video, on my website. Okay, so as we saw at the beginning, whenever we were talking about kind of the concepts of why the integral series works, we basically broke it up into something like a Riemann sum. If you have a convergent series, you need to make sure that your sequence is smaller than that convergent series, right? And that's what we're basically about to do. So here is our series. Now, whenever we go to find the definite integral on this thing, we're starting it actually at 1, right? So this first term that's right here is actually not included in the definite integral, right? Because we're starting the definite integral at 1 and continuing on to infinity, right? So that's why I've broken this first term out of there, okay? So now if I compare just the definite integral, which would be the area underneath the curve, with all of the terms after that first one, I can definitely see that it's smaller than a convergent series, so therefore it must converge, right? So it converges. Fantastic. But now, I've excluded that first term, so I need to put that first term back in there. And when I do, I'm going to see that it's going to be actually bigger than that. So I shifted it over so that you can see that now we're using a left Riemann sum. And even though this is bigger than a convergent, it still converges by the previous discussion. But now we can definitely see when we include that first term in there that it's bigger than the actual value of the area underneath the curve, okay? And specifically, like if we go back to that result, it was pi squared over 6 that Euler showed to be true. Pi squared, pi is about 3, 3 squared is about 9, 9 over 6, definitely it is bigger than 1. All right, so that concludes our lesson on both integral and p-series test. So in order to perform this integral test, remember that you have to have positive terms and you're replacing it with a function that must be positive, continuous, and decreasing. And then you take yourself the improper integral from 1 to infinity of that function, and whatever it does, if it converges, your series converges. If it diverges, your series also diverges. And then the p-series, you just take a look at the power p. And if it's bigger than 1, your series converges. If it's between 0 and 1, including the number 1, then it diverges.